Today we are going to present the paper graph structure of neural networks. So the first question we're going to ask is why would we try to use a graph to represent a neural network? Traditionally, scientists and scholars use computational graph to visualize neural networks. The computational graph can directly show the data flow. For example, in a neural network, neurons are represented as nodes and directed edges link neurons in different layers. Such graphic representation could be used to demonstrate how the network passes and transforms information from its input neurons through hidden layers all the way to the output neurons. And the performance highly depends on the structure of neural networks. However, there is currently no systematic understanding on the relation between a neural network's accuracy or its performance and its underlying graph structure. Most of the time, we need to tune the model or change the underlying structure many times manually to achieve a better performance. There has some limitations of the aforementioned computational graph. The first one is lack of generality. First, computational graphs are constrained by the legal graph properties. For example, computational graphs have to be directed and acyclic, which is a DAG graph, the data flow from input to output in one direction. The second one is compared with realistic biological neural networks, which have a much richer and more complex structure. There are information exchanges between neurons rather than just single directional flows like a DAG graph. And also in the brain networks, such biological or neurological models cannot be simply represented by directed acyclic graphs. Here is an example of computational graph. This is a computational graph of multi-layer perceptron models. As this figure illustrated, the computational graph of such model can only be DAG graph. We can clearly see how the data flows and how to use backpropagation to update parameters along the links between neurons. Hence, computational graph is a very intuitive way to represent neural networks. In conclusion, the computational graph is good to represent neural network, but it is difficult for us to investigate how the structure affects the performance. Hence, the authors propose relational graph to represent neural networks. We can represent one input channel and one output channel together as a single node in the relational graph. As an edge in the relational graph represents the message exchange between two nodes. The link between nodes are not just the data flow anymore as in the computational graph, but message exchange in the relational graphs. For example, in node 1, in the computational graph, there's a input 1 and output 1, and hence in the relational graph, we have a self loop of 1 because we combine them together and their input and output in between itself. Secondly, the graph does not need to be DAG anymore, and we can gain some similarities with neuroscience bidirectional information exchange if we use relational graphs. So, thirdly, one neural network layer corresponds to one round of message exchange over a relational graph. Compared with computational graph, the data flow just from one layer to another layer. But in the relational graph, it will be one round of message exchange for all the nodes. So, hence, to obtain a deeper neural networks, we just perform message exchange over the same graph for several rounds. Here are some examples about how the relational graph works. So the first one, we have 1 as input, 2 as output, and 2 as input and 1 as output. So there will be just a single link in between 1 and 2. And here's another example, which is from 1 to 1, 2 to 2, 3 to 3, and 4 to 4. So there will be 4 self loops for each node. For this example, they have the self loops, and they have the links from 1 to 2 and 2 to 1, 3 to 4, and 4 to 3. So we just link 1, 2, and 3, 4, and added 4 more self loops. So here's an example. The only difference is 1 does not connect to 3, 2 does not connect it to 4, and 3 does not connect it to 1, and 4 does not connect to 2. So there is no this cross line of this graph. So right now we have the basic definition of how the relational graph works. There's still 4 components to construct our final relational graph. The first one is node features. So for each node, there's the node features x, and these node features could be the length or the dimension of the node features could be varied for each round of our neural networks if we instantiate a relational graph. The second one is the message function. Message function is just takes the node feature as input and output the new message so that the node can send the message to all other nodes. Or actually, for each one node, they will receive the message for all other linked nodes. The third component is the aggregation function, which is used to sum over all the messages together and add some nonlinearity to our model. And the fourth one is the number of rounds, how many rounds we exchange the information. In the instantiated neural networks, which is how deep our model is or how many layers we have for our model. Things would be a little bit different if we have different node features. In this example, we have just the node feature just a scalar. But in this example, in the example for the ResNet, and our input become a tensor, which is actually image. So how we deal with this? We just have how we perform convolutional on the relational graph. So which actually didn't change much. We only need to, for each node and link, we would have a new convolutional kernel and perform it on the message function. So we have the definition of relational graph, and we want to investigate how the structure of the model affects the performance. So we have 3 more things to do. The first one is how we measure the graphs, how we compare different graphs. So the authors, they use average path length, which is the L, and the clustering coefficient, which is the C, to characterize graph structure properties. Specifically, average path length measures the average shortest path distance between any pair of nodes for a graph globally, and the clustering coefficient C measures the proportion of edges between the nodes within a given node's neighborhood divided by the number of edges that could possibly exist between them. Hence, it captures the locally features. And the second important thing we need to do is how we instantiate from a relational graph to a model. The author proposed the WS-flex method to generate various types of graphs with respect to the degree of nodes. And the third one is a way to control the computational budget. Because we want to compare the performance of different models, we need to want to make sure that it is important to ensure that all the networks have approximately the same complexity, so that the difference in performance are due to their relational graph structure rather than something else. So they try to control their flops, which is the number of multiplication and accumulation, to be similar to each other for different graphs. This is an example of the WS. This is the illustration of WS flex method. As you can see, uh, as on the left-hand side graph, there are many different methods to generate different types of graphs. And but for the WS method, this method can generate various graphs with respect to graph measures, which are the C and L we mentioned before. After we have the three important things, and we can use the heat map to find out our result. So on the left-hand side, which just all the graphs that we have, and on the right-hand side, which is the axis is the C and the y-axis is L, and the color represents how good for a specific model it is. So they use the matrix top one error rate to show this. The top one error rate, which is for the highest probability of class and the error rate it can get. So there's another very important concept in the paper, which is the sweet spot. By downsampling the graph into a coarse graph, we can find the sweet spot, which is the best performed models here. So this is the sweet spot, and for this one, they just use the 5-layer MLP model on CIFAR-10 dataset, and so to compare the difference in between models, and they did various types of models to compare how the sweet spot would change based on the structure of the relational graph. So this is called consistent cross architectures because we can change dimension of node features for each rounds and the different aggregation and measure functions for each rounds of message exchange. So relational graph defines a shared design space across various neural architectures. In short, different types of neural networks may have some structure, may share the same structure relational graph. As this 5 image shows, we can observe that relational graphs with certain graph measures, which means they have the same clustering coefficient and average path length, the sweet spot may consistently fall into a specific range, regardless how they instantiated. For different neural networks, the sweet spot always fall into with a range of, for C is 0.43 to 0.5, and for the average path length, it will fall into 1.82 and 2.28. There's also another consistency with respect to different tasks. This is a correlation of the top one error rate values across different pairs of tasks. So for example, the first task is 5-layer MLP, and the y-axis is the ResNet. And we can find that, and there are linear relationship between them. So for a specific data point in the graph, which represents a specific structure of a relational graph, and the x are top one rate. There's also some interesting findings based on the relational graph. As we have mentioned that there's some limitation of the computational graph. For example, they cannot represent the complex neuroscience networks. When we use, and another thing is that the sweet spot always falls into a specific range. So the interesting part is the best performing relational graph the graph within the sweet spot, which is the graph within the sweet spot, that they discover surprisingly resemble biological neural networks, as shown in this table. So as we can see, for the MEDAC whole cortex network, they have the average path length as 2.38, and the clustering coefficient is 0.46, which is very close to the relational graph that we generated, which is the best relational graph that they generated, which is 2.48 and 0.45. So in conclusion, the structure signature of the well-performing neural networks always fall into some range, and this is, I think, is a good thing to say. They make some progress to investigate how the structure affect the performance of neural networks. By structure, they use the average path length and the clustering coefficient as a matrix. And they also find an efficient way to check whether a given neural network is promising or not by simply checking the clustering and the clustering coefficient and the average path length. And also, they also build the link between neuroscience and the deep neural networks, as this table and the image shows. But there is, in my opinion, there is some limitation. There is some limitation for their experiment. First, they use the top one error rate rather than accuracy, and the top one error rate with just the top one sample error rate. So, which is, I don't think is as good as to compare the general accuracy for the whole data set. So that's it. And thanks for your listening.